Okay.
Okay, welcome everyone to HO Colloquium today by Chris Osborne. It is my great pleasure to introduce Chris Osborne. Chris Osborne is a RAS Norman Lockyer Research Fellow at the University of Glasgow, developing techniques to merge modern non-equilibrium radiative transfer for magnetohydrodynamic modeling to study the formation and evolution of cool condensation in the solar corona. Chris obtained a PhD from the University of Glasgow in 2021 on radiative transfer in solar flares and has also worked as a research software engineer. Today, Chris will be speaking on towards the next generation of non-equilibrium solar radiative transfer. So please.
That's great. Thank you. Yeah, it's great to be presenting to you again. I think I gave one of these in 2019, and it's great to be doing it again. So I'm going to be talking about non-LTE radiation primarily in the visible, in the sort of classical spectral line region of sort of the UV through to the infrared, that sort of main visible band. So I imagine that most people will be familiar with non-LTE radiative transfer, but to give the very brief overview, it's the complicated situation we find ourselves in when dealing with sort of the spectral lines of interest, targeting the sort of cool but not too cold plasma, all the stuff that forms in the chromosphere and in the coronal condensations. And it's most of these transitions are very complex to model in the sense that knowing the state of the plasma alone is not sufficient to determine emissivity and opacity coefficients, and instead the global radiation field influences these things. And there is quite a lot of there are these potentially global interactions that affect ionization and excitation. And really, this is the only way to model these spectral lines, which is the only way to correctly evaluate radiative losses in these regions for things like modern MHD models, and also for the sake of inversions and figuring out sort of what atmosphere we're looking at when we have a particular observation, we need to be able to understand these lines. So I'm showing on the right there a Hinode BFI image of a beautiful hedgerow prominence. And one of the sort of my neat little comments on this is that if we took the sun away but kept the prominence there with all the sort of plasma parameters the same, and we took the solar disk away, that structure would be nigh invisible. You wouldn't have the signal to noise to be able to detect it on any kind of sane integration time, and that's simply because there isn't enough emission just sort of due to the thermal nature of this, and that global radiation field is really sort of visible in action here, and we see the scattering of light coming from the disk, but also it pumps the structures internally so that we can actually see them and image them. And I think this is a very tangible way to sort of understand what's going on in the sort of non-LTE model that we all talk about. So yeah, there are many spectral lines and these spectral lines probe somewhat narrow regions, but as I was saying, they are affected by they couple multiple regions together, and it's disentangling this that really sort of gives the complexity, but also the magic of this style of modeling. So when we're looking at solving the sort of the non-LTE problem, it boils down to this, which is that the radiative rates, the thing that we need to determine the ionization and the excitation distribution of atoms in the plasma, ions in the plasma, is dependent upon the intensity hitting that particular parcel of plasma. And you need to integrate up over the 4 pi solid angle in all directions. But in turn, that intensity is dependent upon the radiative rates elsewhere in every other packet of plasma that you're considering, because they all influence each other. And we distill that down, I would say sort of the most important quantity is obviously the specific intensity, but more importantly, the thing that we end up needing the most and to have the most accurate evaluation of is its first moment, J, which is sort of the angle averaged integration, the angle averaged radiation fields, the angle averaged intensity at a particular wavelength at a particular point. And that's because that's the term that appears in the radiative rate when we're evaluating the radiative rates. That's the term that effectively gives us the pumping radiation field that we need. And these are high-dimensional functions, and that really is the problem. When we include sort of the wavelength dimension, neglecting any kind of time component, assuming that the speed of light is infinite and everything settles instantly, we're still left with a 6-dimensional function for intensity and a 4-dimensional function for its first moment. And so those are very serious and in many ways irritating functions to deal with compared to sort of the more 3-dimensional nature of the MHD equations, particularly when we include that sort of global coupling. Things don't just, there's no sensible sort of CFL we can apply where things only affect adjacent neighbors. Instead, we have this global problem everywhere. So the current radiative transfer methods we used were developed essentially through the 1950s through to the 1980s, predominantly. And they were built around the idea of smooth atmospheres primarily. But the atmospheres that we end up solving for when we look at our modern MHD simulations look more like this. This is a snapshot of a levitation condensation prominence model. Or this is Bifrost. That doesn't look overly smooth to me. Particularly sort of the regions we're interested in for these very high opacity lines, like the Heischen-Lyman lines that form higher up in these highly corrugated surfaces. And the same there, that's a Murram chromosphere cut. There's a lot of complexity, and there's definitely not necessarily smoothness there. And if we go to observations, we see very much the same. In particular, I'm going to start in sort of talking about flares, and then I'm going to move on to my more current stuff, but it really does all tie together. And longer term, I'll come back to flares. I just haven't got there yet, but there's a plan here. And so this is a fantastic BBSO observation. There was a recent DKIST one that did the same higher resolution, I would say. So this is looking at post-flare loops in H alpha and measuring the kernels that we were seeing. It's obviously at the limit of the instrument, but we're talking about structures less than 100 kilometers. And so this got us thinking. This was back at the end of my PhD a few years ago. We were thinking about, okay, so what does it mean? We do plenty of flare modeling using plane parallel one-dimensional codes, RADIM, for instance, HYDRAD's another, FLARIX. These sort of codes treat the atmosphere as a hydrodynamic flux tube, and they solve for radiation through it, which is great. It has all the essential physics we need. However, they're working in a plane parallel radiative transfer assumption. And in that sense, we are assuming that the extent in X and Y, so perpendicular to the sort of the stratification direction of these one-dimensional models, is infinite. So we're assuming that the size of a flare kernel is infinite. But when we're looking at something like these tiny, fine tubes, it's clearly not, and it's clearly surrounded by material that isn't at the same temperature. And so what effect does that have when we're solving the radiative transfer? Because we're not just assuming it's a fine vertical thread, we are assuming it's a infinite extent vertical thread. So we went about putting together the simplest two-dimensional model we could come up with that sort of tied this together. And so what we did was we took a time-dependent atmosphere from radon in this case, and we put it in in the center of a quiet sun slab. So we effectively assumed that we had a flare going off into the center of a quiet sun slab with the same atmosphere as the radon model started from. And we varied the widths of this kernel that we put in, and the quiet sun region was fixed to have no evolution in terms of fluid flow. But so all we were considering really was the sort of the radiative effects on it. But we were considering ionization, and we see very significant pressure gradients that mean that we certainly should have flow, but the model didn't include them, as we were purely sort of considering, okay, what do we get from radiation alone, with the hope of coming back to look later at at flows, but also there's no effect on this central thread, which is something that longer term needs to be looked at, but we're not quite there yet. So I'll just jump straight to the results of this. And so what I'm going to show you is effectively what happens if we have a slit spectrograph looking straight down from the top at this model. So this is for the H alpha line. I've taken a few cuts. So on the left, we have the image. We heat the atmosphere for 10 seconds, and we have cuts. And in pink, on top of these cuts, we have what the equivalent radon atmosphere, if we treat it as just being plane parallel, looks like. And even in the center of the heated region, which is the blue line there, they really don't look the same. Now, okay, this was a small kernel. This was 125 kilometers. This is quite small. I mean, our observations predict that in many ways they are smaller than this, but okay, this is certainly testing the limits of comparing plane parallel models to multidimensional models when we've got such high energy injections as something like this. Okay, so let's look at a thicker kernel. So in this case, we're going to look at the calcium 8542 line using a 500 kilometer kernel. So way bigger than we see in many ways. And looking at the blue cut, comparing it to the pink cut, it's not so bad. There's definitely differences, but it's not particularly during the main heating window at the start. It's not so bad. The reversal in the center is more pronounced, and the blue wing there doesn't rise quite so high, but it's closer than H alpha. So as we make this wider, clearly we're approaching the plane parallel limit, but we have to get really quite wide to do so. So I've just highlighted here for a couple of times, in this case, the H alpha line at late times, where we see there's really quite a big difference in the blue wings. The asymmetry is very different for that blue line versus for the pink line, which is just the single radon strand by itself. And then I picked an earlier time for the 8542 one. So in this is just after we've turned the beam off. So the beam ran for 10 seconds, in this case, the electron beam that was heating the atmosphere. And here we have quite a significant difference in line shape, really. It just fails to fill in this blue wing component, despite the fact that the thermodynamic properties in the heated region, so this 500 kilometer region here and this 125 kilometer here, are identical to the plane parallel model that we have in radon. Okay, so we have tools to try and understand where this is coming from. So let's start with the contribution function, for instance. And so the contribution function here, well, in fact, really the more important thing rather than the contribution function in this case is really just looking at the tau equals 1 surface for this particular line. So this is for the calcium 8542 line. And the tau equals 1 surface moves by several hundred kilometers. And so up here, the tau equals 1 surface arrives at about 1.5 megameters in the model. And that's for the 125 kilometer kernel. As we go bigger, yeah, that blue wing, it does push down a bit, but it's still a long way away. It's still 300-400 kilometers higher in the blue wing, even at a 500 kilometer kernel size than it is in the plane parallel model. So this assumption of infinite horizontal extent is potentially problematic when we're actually trying to predict what these ribbon structures look like when we're actually imaging these. And okay, well, lines are forming in different regions. So should that have any real effects on the dynamics of what's going on in the actual flare kernel itself? Obviously, radiatively heating the quiet sun region next to a flare kernel should respond with dynamics that we neglected in our model to get this simplest possible model. But these are quite significant differences in radiative losses coming from the center of the kernel, where the thermodynamic properties are, again, identical to the radon one. I've highlighted a few regions here, and this is a log plot with a very large range on it. So we see really quite significant differences, even though the lines aren't actually spread that far apart. This is for that case. That time we were looking at with the calcium 8542 line, where we just turned the beam off, and the upper chromosphere cooling rates vary quite significantly. And here, this is the late time, where the plane parallel model throughout this whole upper chromospheric region has a different sign in its radiative loss versus gain function than the 2D models do. So there's certainly limitations there, and this is something we were thinking about. Okay, so we need consistent, tractable 2+D modeling moving forwards. These extra dimensions are important for diagnostics, but it also looks like, from our sort of first order model, if you can call it that, it might be a 0th order model, it looks like these effects are going to be important for the dynamics. And one of the things that excites me about radiation, particularly in flares, but you see it in structures such as that prominence at the beginning, is that radiation as a mechanism is something that lets energy propagate that is completely free of the magnetic field. And we don't have much of that in solar physics. Almost everything's tied to the magnetic field, but here we have something where it doesn't really care about the magnetic field. It obviously cares about the optical depth between 2 points, about how much of it is absorbed. But if there's line of sight to some degree, then it can influence the other. So this is sort of motivating what we're going to be coming to. An interesting sort of mini result we came across in this is that the filling factor you get, effectively how far the line diffuses, is really quite wavelength dependent when you have a fixed atmosphere next to it. The line core typically diffuses much further into the adjacent region when you're looking at how is the spectrum influenced than the wings do. Presumably because it's carrying more intensity in that sense. And that's something interesting that needs more analysis for the sake of sort of future diagnostics. Yeah, so we can clearly see that there's some notable limitations to these plane parallel models that longer term we need to look at sorting out. And there's a reason why this second, why the models I've shown you here. So we did some earlier work where we took the radium model as a boundary condition rather than putting it in the center of the slab. And that work was published a few years ago. But this second lot never quite made it. And it was because there was a few issues in the way the radiation field was being treated that I was never quite happy with. And these are going to crop up later, so remember those. I won't say any more on them right now, though. So now we move to sort of the second part of the talk, which is very much my current focus of research, but it does all tie together. So some of you may be familiar with this image. This is a very famous image in the world of computer graphics. This is the Cornell box. So this was effectively the original test case for photorealistic rendering of images with a computer. It's fantastic in the sense that you illuminate it with a known source of a known size. The walls are painted or are colored a known color. And so you can build a copy of this box in real life, take a picture of it with a known camera that's been very carefully measured. And at that point, you have a reference pixel value for what for when you render this, including all the bounces of light around this scene. So the white light bouncing off the red, lighting the side of this box here, and bouncing off the green and here, and all the various shadowing, the widths of the shadows, how much these sort of semi-shadowed regions are actually shadowed. You have effectively a perfect reference for this that you can then try to reproduce. And this remains sort of the standard test case for a classical ray tracer, path tracer that is used in computer graphics for this reason. But really, in some ways, a lot of what's going on is the same as in the sort of the wider astronomical field, the things we look at. Ultimately, the physics of the light is the same. So this is a potentially slightly different representation of the radiative transfer equation to how you normally see it written down. it's one that sort of, to some extent, ties the two fields of computer graphics and astronomy together, in that I've stolen bits of their notation, and some of it's in bits of our notation. But I think what it does is it highlights quite nicely the nastiness of the equation, in the sense that this is a recursive integral differential equation, meaning that L, the thing we're interested in, the radiance, which radiance is a computer graphics word for specific intensity, the radiance that we're interested in appears as both a differential quantity over here and an integrated quantity over here. So it's really not nice to try and solve for. And in the general case that I was discussing at the beginning, where effectively we have these the contributions of the radiative rates to determining the emissivity and the opacity of the plasma, these chi and eta terms are also dependent upon the radiance itself, or technically on this integral over solid angle of the radiance, without the phase function in this case. Although the phase function comes in when handling strong lines in things like partial redistribution mechanisms. So it's not a nice equation to solve in many ways. And this was something we butted up against in a project I did with Jack Jenkins 2 years ago now. So we thought we'd been modeling 1D prominences. So we were taking the output of MHD models, we were extracting them column by column, effectively, and modeling them as a filament. So we had a lower atmosphere, and then we had some filamentary material in the corona above it. And then we were solving plane parallel 1.5D radiation synthesis, because we just wanted to get an idea of what the lines looked like from these models, and sort of try and apply the sort of chromospheric synthesis techniques that have been used to sort of the prominence modeling that the AMR-VAC group in KU Leuven were doing at the time. And we kept getting this very concerning thing of filaments that were brighter than the solar disk. And it turned out what was happening was that it's the same as I sort of opened with saying in the Radin models, the sense that, oh, it's plane parallel. We're treating these as infinite slabs along the axes perpendicular to our axis of stratification. So if we're stratified along Z, X and Y are infinite. So what that means is any radiation that wants to escape the chromosphere in this case has to hit the bottom of the bottom of this filament structure. Now, by just the general rules of how this works, radiation that's absorbed there will be emitted by spontaneous emission primarily, and spontaneous emission is an isotropic process, meaning that for a static particle of plasma, 50% of the radiation that is absorbed will be spontaneously re-emitted back down. So what you've done is you've actually successfully created a not very efficient, 50% efficient laser cavity. And so you end up repeatedly pumping the radiation by trapping it between these two, between the lower chromosphere and the body of the filament. And obviously, that degree of trapping is completely unphysical and was a pure limitation of the model. And so we moved the chromospheric component to a boundary condition, and moved on and got sensible synthesis that agreed with everything else that was out there. But it left a question, and the question was, okay, so the albedo is real. The effectively the spontaneous emission scattering a significant fraction of the intensity back down off these structures is real, because the physics is simple. It made sense, and clearly they take up some filling factor of the sky above you if you're standing on the surface of the sun looking up, and will be quite efficient reflectors in that sense. And so we tried to set up a nice little 2D toy model that would show this, that would capture this effect and actually let us quantify it. And here is the result of that 2D model, which is a excellently realistic square blob of a prominence floating in the sky above a perfectly flat, plane parallel, infinite, quiet sun atmosphere. Highly realistic stuff. And this took massively much longer than it should have done. This was accidentally months of work for what looks like a toy model, because we kept having issues with getting sufficient angular resolution in the radiation field such that the coupling between all of these regions down here and this effectively quite small blob up here was physically accurate, and that energy was nicely balanced everywhere, and that we weren't just getting we weren't just getting sort of we weren't seeing accidental effects that were just due to limitations of our numerical method, but were actually provably of the structure itself. For instance, if we just had beams that were coming out over here that were missing and others were hitting at you, we would get brighter and darker patches. Particularly here, this is the electron density, and we see here that in actually the upper chromosphere, the electron density is actually enhanced by a factor of over 100% in for a significant component, and that's just because a large amount of the photoionizing radiation is reflected off the structure back down into the chromosphere. And so ensuring that this was all integrated correctly was really difficult to do with the sort of standard short characteristics methods. And we ended up using, for those of you who are familiar with these things, the default quadratures typically use 3 rays per octant would be quite standard when you're integrating over the unit sphere, 3 rays per octant. If you're being fancy, you might go to 6. There are some quadratures out there, particularly for those of you doing scattering polarization, for instance, where you'll be using 11, 12, that sort of thing, maybe 20. Yeah, this we had to go to 96. And it was a horrible bit of computing that made us do it, because our code wasn't designed for that at all, because nobody builds a code for that number of rays. That's silly. So we set up some toy test cases after that. And so part of what we ended up with was the fact that these models, the techniques we're using, short characteristics, for instance, that were developed for this sort of astronomical radiative transfer, effectively assume that the medium has quite a lot of scattering in it. So we set up some purely toy models where we had emissive blobs at different wavelengths in a volume, where most of the volume has no scattering, and then there's a centrally region with some scattering, and then some little blocking components, etc. And we used a very high order quadrature. This was, I think, 11 rays per octant, which is about as high as is ever commonly run. And we see lots of ray effects. We see lots of obvious ray structures that really shouldn't be there. And so what should the solution to this problem look like? So the solution to this problem should look nice and smooth like this. We see that this little structure here is casting shadows relative to the different light sources. This one here, which is strongly absorbing in red and strongly absorbing and emitting in both red and blue, has a very obvious red shadow over here. A shadow in its red channel over here, for instance, and this scattering region is correctly reproduced. And so we wanted a method that could get us to this. Now, the field of computer graphics has a method, which is the default one that they employ for this, which I skipped past earlier, but that is effectively Monte Carlo path tracing. So this is the default technique in photorealistic rendering nowadays. And it works fantastically. It will get you a beautiful result. It will also take an inordinate amount of a huge number of samples to get there. So the image on the left is taking 8 samples per pixel. So if we effectively set up our camera, and then from our camera sensor, we shoot rays forward with some random properties and bounce them around the scene, collecting all the light they go through, including things like handling, in many cases, refraction off the glass structures over here. and we do that 8 times for each pixel of the image, we get this horrible grainy mess. If we do it 8,192 times per pixel, we actually get something really nicely converged and beautiful. And this is the sort of the core technique that's used in rendering movies and whatnot, and is starting to enter the realm of real-time graphics thanks to big push from NVIDIA and people in terms of their RTX hardware that's really trying to push ray tracing into a more modern or a more tractable standpoint for many uses. But yeah, the issue is really the convergence rate of this, and the convergence rate of Monte Carlo path tracing in general cannot be better than 1 over square root number of samples. So, or the error rate doesn't drop faster than that. So the convergence is poor, meaning that in complex structures, a lot of rays will always be needed, and that's difficult when we need to iterate through these structures many times to correctly integrate at high optical depth the radiation field to solve for our secondary problem, which is determining actually what the emissivity and opacity are through the radiative rates. Because in these scenes, we're assuming everything's known. So we're solving for the image once. We're not solving for the image or the volume hundreds of times like we have to do for the non-equilibrium problem. And that's why deterministic methods like short characteristics have primarily been employed for the solar case, particularly given the high optical depths we get to. So one of the sort of obvious, we wanted to know if there was a middle ground between sort of tracing lots of random rays, which has to have poor convergence rates due to the randomness, and the sort of these non-stochastic methods, these deterministic methods, such as short characteristics. And I've been a sort of graphics programming hobbyist for many years. I really like the science of it, and sort of seeing what you can produce in as close to real time as possible. And you look at modern video games, for instance, and you go, well, actually, they're solving more and more true realistic physics, light propagation physics problems hundreds of times a second, certainly tens of times a second. And certainly they're not considering strong spectral lines at many wavelengths, but the physics of the radiative transfer equation is more or less the same. So, okay, let's look at what they're doing. And as an interesting aside, obviously, if you're looking at anything in that sort of field, you are working on GPU. It's the only way to do these things. And one of the very interesting things that come up as you start to dig into GPU programming and do more than simply, oh, this is a massively parallel for loop where I run every iteration in progress in parallel, is you start to realize that actually, oh, these machines behave much more similarly to the old vector supercomputers than they do to any other piece of hardware. And quite often you can sort of revive old methods that were sort of published for the old vector craze and whatnot. And they run fantastically on modern GPUs because actually the hardware behaves quite similarly at the end of the day. Much more than, say, trying to port a classical MPI CPU method to GPUs, which can be a much harder endeavor if it's more than sort of just a parallel for loop. So we got there in the end. We published our method for doing this, which is the one that I used to show the reference, the so-called reference solution earlier. And this is, to my knowledge, the first and still only paper co-authored by astronomy and a video games company, which we're really quite happy with. So I'll walk you through a bit how it works. So our sort of motivating argument, which is what we use to construct everything, is that if we have a linear light source, just a straight line of light that illuminates a plane, then anywhere where you are on this plane, the amount of light you are receiving is proportional to the solid angle of that light source. If we then add an opaque blocker at some point, then we have a fully illuminated region where nothing has changed. We have a fully shadowed region where no light from this can arrive. And then in the middle, we have this semi-shadowed region, which is called the penumbra. And we're just going to annotate this and make a few observations as a result. So first observation, these are really complicated things. You need approximately a best high school maths to handle this, is that the further away you get from the blocker, the wider the penumbra is. This is purely a geometric consequence of light propagating in straight lines. Secondly, well, we actually need to be able to resolve the size of the light source. That's what kind of follows from the fact that if the light at a point is proportional to the solid angle of the light source, well, then we need to be able to resolve the size of the light source. And so at distance A, the light source subtends an angle alpha, and at distance B, it subtends an angle beta, and beta is smaller than alpha. There we go. That's the observations that we end up needing. But when we make some small angle approximations and do a little bit of shuffling after this, we derive some criteria that we refer to as the penumbra criteria, that are the criteria that are necessary to correctly reproduce the penumbra, because the penumbra has an interesting quality as well, which is that along any straight line parallel to the blocker, such as A or B, the radiance along it varies very close to linearly as soon as you're a little distance away from the blocker. So we can pretty much go, oh, there's a linear ramp in intensity from one end of B to the other end of B here. And so that means that actually, well, if we just have a sample at both ends of B, and this is our only light source in this case, then we can actually almost perfectly reconstruct the radiation between the two. And so we end up with these sets of criteria that let us discretize the radiation into shells around the point. So in this case, we just take what are the contributions from this shell, and then we take a shell further out where we have a different scaling law. We use a different angular sampling, and we use a different spatial sampling. So we cascade these probes where we sample around ourselves at high spatial resolution but low angular resolution. And then we go to slightly lower spatial resolution and slightly higher angular resolution, and looking a bit further away from our central point, so sampling from the center of each of these. And we keep doing this. And we build up a structure that effectively encodes in a sparse way all of the radiance information throughout the volume that we're interested in. And what happens is we can actually merge these and interpolate them in general. So this set of cascades that we have fully sparsely encode the full quantity that we're interested in, which is both the angular variation of the intensity, but also its first moment J. By definition, if we've encoded the angular variation, then we have to have that first moment J. But by the nature of how we constructed this and the fact that penumbras vary approximately linearly across themselves, we effectively have also thrown a Nyquist criterion in. And so we end up with something that we can interpolate without aliasing. And that's due to the fact that when we sample these further away contributions, we're doing so at high resolution, but we're not including any contributions from stuff nearby us. So we're not oversampling anything near us, and we're only including distant contributions necessary to solving the equation that we're interested in. And it's this fact, it's sort of this Nyquist criterion that we end up with that makes this useful. And it's a very intuitive thing in the sense that if I'm nearby to something and I'm living in a discretized world where something has a minimum size, then it's going to be quite big if it's near me. So I don't need much angular resolution to see it. However, if I move even just a little step across, effectively its influence on me changes dramatically. Whereas for distant quantities, they will be very small. I need a good angular sampling to see them, but I'm pretty unaffected by moving laterally relative to them. The parallax is small in that sense. We are also able to pull other concepts from computer graphics. For instance, the concept of MIP maps that they use, which is a effectively local recursive averaging term, which we were able to use to accelerate our solution further. So radiative transfer doesn't mesh well with traditional adaptive mesh refinement techniques that are used for things like MHD, because different spectral lines form in different regions and require resolution in different regions. And so by the time you've refined for this line for one thing, and this other line of the element, you've ended up refining everywhere and not gaining very much. And it's very difficult to build a sort of classically adaptive scheme unless you just have a lot of free space, where you just go, okay, yes, well, clearly there's nothing there because there's 10 hydrogen atoms per cubic meter, so it's probably not worth having a very high sample rate there. But in regions where that's not the case, what we did was we built these structures inspired by the OpenVDB library, which is, to the best of my knowledge, it is the only code library to have ever won 2 Academy Awards, which is something we built on for that. We built a modified version inspired by their work for efficiently representing sparse volumes at multiple resolutions that allow us to ray trace through these structures very efficiently. And the construction of these compressed resolutions gives us about an order of magnitude speed up when we're actually integrating all of the rays that we need for our cascades. But the actual cost of constructing the volumes is a trivial component of our overall calculation. And so as a result, we're able to fully update these as we solve for a particular model. So here I'm showing the different resolutions, which eventually settle the regions where they're needed, but otherwise are determined purely by the atomic population variation and the variation in emissivity and opacity in a particular region on the fly during the calculation that we're doing here. So I'll show you some science, because we made it to the end. You made it through all of the sort of the scary maths, the simple maths and the scary computer graphics bits. So end result is that combining all of these techniques together allows us to solve for this very high for a snapshot of this very high resolution model for simultaneously for hydrogen, calcium, and magnesium using very high wavelength resolution models in about a day on a single NVIDIA H100. This method scales perfectly well to multiple GPUs, but that's the sort of compute time we're talking about. And the scale of this model is about 1024 by 768 by 384, I think, or 512. I can't remember off the top of my head. And once we've solved it, we can reproject the model from any viewpoint, which is very useful, and it's how we construct movies like this one. So this is a wonderful filament simulation, prominent simulation from the KU Leuven AMRVAC group. So this is looking in Lyman beta. This is a COCO plot. So what I mean by that is it's color compressed. So the green represents the line core, the blue represents the blue wing, the red represents the red wing. So we see asymmetries appear, we see oscillations, and then I've put a slit down the center of the image here, which I'm showing over here, showing you sort of some of the variety of spectra that pop up. And I think the key takeaway here is that there's a huge variety. So we start out looking up at this prominent structure, and now we're seeing it from looking up, sort of up from underneath, but our camera is rising. So now we're looking from the side, and then we end up looking down against it as a filament against the disk. And we can do the same for the iris magnesium line. So this is magnesium K. And we see overall, yeah, I mean, obviously the bulk red and blue trace the flows in the structure. Nobody's surprised by that. Sorry? Did somebody say something? No, I'll carry on. Yeah, there's a lot of variation in profiles. Particularly you see projected against the disk, there's a lot of variation in profiles there. Okay, let's actually do something scientific rather than just watch movies spin. So here they're a little bit difficult to pick out, but corresponding to each one of these line colors, I've marked an X across on the plot. So there's red, orange, green, and blue. And they correspond to these line profiles in H alpha, calcium 2K, magnesium 2K. So spectral lines, yeah, we see weird complex profiles when we look down the spine of this structure. But we're looking down the spine of this structure without looking quite perfectly down the spine of the structure. We're very close to axis aligned, but not axis aligned with the field, because the field here, at least the bulk component of the field, was effectively built into the simulation in a pretty axis aligned fashion. And what I've done here is I've rotated the model by less than a degree. And I mean, for H alpha in particular, yeah, those lines look quite similar. oh, but the number of peaks in calcium 2K has changed, particularly this red one, and this blue one here has gone from this sort of 3-hump one here to this 2-lump one here. And then magnesium has gone, well, completely different. Okay, that's interesting. Okay, let me do another rotation of less than a degree again. So these are very small twists. I mean, you can see at the bottom that the structure is moving just a little bit. The points are staying as aligned as I can make them, in the sense that they are aligned. Their position aligned such that their ray passes through the center of the structure in the exact same point. But of course, the structure is long, and so there is parallax down the structure. And so there is a lot of complexity. And now even, oh, the H alpha looks different, particularly these red ones. And this blue one here, the Doppler shift has changed quite dramatically. But this was such a small rotation in that sense. And my takeaway from that really is that a lot of the radiative post-processing that we've seen of all of these sort of complex 3D models has always been axis aligned because it's the easiest thing to do. We synthesize at mu equals 1 and we go, okay, this structure looks like this for the most part, particularly when we get to these sort of these optically thick lines, these chromospheric lines, these lines that are hard to model. For sort of AIA stuff where you can integrate, or optically thin diagnostics, we've had a lot more stuff where we view it from different directions. But it hasn't been done so much for these lines, but there's a world of complexity that turns up as soon as you sort of break this alignment. Additionally, I just want to encourage people, and I think this audience at least is going to be more on board than many in that sense, to really encourage you to look at sort of interdisciplinary opportunities. In this case, the computer graphics input came from the fact that I knew people online from sort of hobby work. And we eventually realized that we were all talking about the same problem in different words. And that's a really difficult thing in interdisciplinary work, in that you need to develop a common language, because everyone's been developing methods to solve similar problems off by themselves, and they've come up with slightly different names for it. But radiance cascades is sort of a very powerful and interesting tool, I would say, for non-LT radiative transfer. And it's sort of one of the first big changes for the sort of intensity only problem. And the bulk of development of it came from outside the field and continues. There's a lot of active sort of hobbyists in the computer graphics space who are interested in improving the solution of this problem and dealing with some of the minor artifacts that it still presents. And we will automatically benefit from that, really. So thank you. And any questions?
Okay, go ahead.
Yeah.
Sorry. Can you hear us, Chris?
Yes, I can hear you now. Yep.
Okay. Sorry, it was muted. So I'll just repeat. Thank you for the nice presentation. Very nice to see. Could you go back one slide just for clarification? I was wondering, in terms of the viewpoints that you have and the synthetic lines on the right-hand side, is this basically like a slit viewpoint, or is this like integrated over the full field of view that you have here?
These line profiles, sorry, no, they are associated with points in the image that I selected semi-randomly. And I admit they are hard to see. I might be able to zoom in. Nope. But yes, so the orange point is here, the red point is here, the blue point is here, and the green point is here.
Oh, I see. Okay, thank you.
So, and it's just, so I keep those points fixed and effectively in the central plane of the structure. And then obviously the front back kind of rotates relative to that. So it's effectively like having the same structure fixed perfectly on the limb, but then just what if the field was twisted slightly differently, how would we see it differently? And the answer is it looks completely different, which is sort of obvious, but also not the way we are used to seeing these diagnostics, I think.
Yeah, thank you.
Phil, please unmute. And...
Oh, yeah. Hi, Chris. Thanks.
Hi.
Thanks for a very interesting and novel talk. If I look at the images you're showing right now and the difference between the different angles being so extreme, it suggests to me that one needs to be very careful about how one chooses the problems that you're going to try and address in the future. The idea of, we've been told at NCAR for years that why can't you just build a model of the sun? I mean,
yeah.
It's an absurd thing to say from people ignorant about the difference between some terrestrial work and this stuff. So, but the point I want to make here is that, for instance, for years and years and years, there's a fudge factor in stellar atmospheres that still gets used all the time called microturbulence or macroturbulence. And the nature of that seems to me to be critical because in so many ways, not just in diagnosing what the plasma might be doing from the radiation, but God help us if it looks like this, because you get a different answer just changing. If the Earth would go another day around the sun, it looks different. Yep. The same structure looks different. So all I'm wondering is what plans, I was going to ask you what plans you have to address certain kinds of problems here. It may be that you go down the route of, more towards the computing aspect and the applications to, movies or whatever it is. That might be much more profitable. I imagine it must be. But in terms of making profitable advances in understanding remote sensing of the stars in particular, and without stars, we see almost nothing in the universe. So the stars still remain the central problem for us to understand the universe. Do you have any solid ideas yet as to how you might be moving forward to really crack some interesting problems?
Well, so for me, these plots here are sort of a cautionary tale about overanalyzing a few choice pixels more than they are a result in of themselves. And it's very much sort of you can get lots of things out, but we are going to have to be careful, particularly as we get to higher and higher resolution stuff, about overinterpreting a single snapshot in a single location at a single time. Of course, it has a wealth of information that we need to exploit, but we can't get too bogged down on what that one pixel is showing us, I think. That's my feeling. As for where I'm going next, so what we're building at the moment is we are coupling these two MHD models to try and get the dynamics of these structures correct, to try and get the true radiative losses correct, the ionization balance correct, and start to see how that affects the evolution of coronal condensations in that sense. Do they form differently when the ionizing radiation field is properly taken into account, including the fact that layers further up are shielded from this field, while stuff down below is taking the full force of it effectively. So that's sort of our primary interest right now. And then from there, obviously, from there, I'm involved in the UK Large Solar Modelling Award that started last year. So we're then going to be looking at sort of how do we bring this back to the chromosphere? How do we sort of capture this physics in an efficient way? Will that reveal secrets of the universe? I don't think so. No. I think that requires a lot more sort of hard thought than the sort of heavy modeling that we're doing, but hopefully it will help give us some good diagnostics for the sun.
Okay, great. There was one other thing, if I can recall it. Oh yeah, I was struck by your statement at the end there, where you we're contrasting the optically thin and optically thick structures according to opacity and the various lines and stuff. And so that seems to be a robust statement that you're making, I would say. Because, you know, I mean, just the thermal emission from, or even some non-thermal electrons doesn't really matter, but the optically thin emission from the corona, then you're not really able to go straight and make a statement about three-dimensional structures in the lower atmosphere compared with the upper atmosphere. The upper atmosphere, you can slice at different angles and do it like a radon transform or something because it's optically thin. But in this case, that's going to be, well, very interesting, and some way down the road, I think. Is that fair to say?
Yeah, it's some way down the road. However, the current work that's going on in our sort of online community, where I have the amateur graphics people and a few physicists of various backgrounds discussing it, is all about doing radon transforms with opacity and whatnot, and trying to determine what the optimal basis for sort of describing the describing J, that a minimally sufficient basis for determining J throughout a volume is when including all of the sort of the physical effects. That's the problem of the moment in that particular space.
Well, you in stating that, you've already answered my first question about what problems you want to go for next. So I think it's wonderful work. I wish you all the best, and thanks so much.
Thank you.
Other questions?
Yeah, I'm wondering, so am I understanding right that you will build these techniques into the simulation and into the energy transport?
Yes. Yes, that's something we're working on at the moment.
And if you do so, and you deal with, say, flare dynamics, you will have to deal with radiation hydro.
Yep.
So a whole new can of worms.
Absolutely, yes. So we're doing radiative MHD right now, but at relatively low energies. We don't have the sort of, we're not having to deal with the flare energies. Longer term, that is absolutely the plan. But we're trying to build it up slowly, which is one of the reasons actually why I turn my attention to coronal condensation, prominences, coronal rain, that sort of thing, is it gives you a slightly more isolated environment to sort of try and get the details ironed out before flares, where there's so much going on.
I'm glad you are aware that in flare dynamics, it's going to be a whole.
Oh, it's a huge challenge. The UK SAMS project for solar atmospheric modeling is a 5-year project where we have, I think, about 30 years of postdoc time, and at the end we're hoping to sort of get to reasonable active region modeling with at least a decent radiation model included in that. Where I don't think that will be flares. I think flares are another 5 years beyond that, if you're lucky.
Yeah. Thank you.
Thanks.
Any other questions from the hall or online? Okay, if not, let's thank our speaker again for a very nice talk.
Thanks very much. Thank you.